Welcome everyone to the talk entitled High Repetition Rate, High Harmonic Generation with Ultra-High Photon Flux, a work that has been actually done at AFS company in Jena, Germany, together with researchers from the Netherlands within the frame of the research project LINX. So in the beginning, I would like to, first of all, motivate our work with potential applications of high repetition rate, ultra-fast lasers, and in our case, fiber lasers. So of course, a very obvious application is found in materials processing, the generation of secondary radiation via high harmonic generation, which is the topic of this talk. And then for high energy systems, also particle acceleration becomes of interest. So that means on the one hand, you need high peak power or high energy to enable those applications. And you need high repetition rates, which corresponds to high average powers to increase speed, signal, and noise to signal to noise ratio in your applications. So as I said, in this talk, I would like to focus on high harmonic generation, and let me briefly say a few words on this process. Here you focus an ultra-short laser pulse into a gas target to intensities typically on the order of 10 to the 14 watt per square centimeter. Then you generate secondary radiation via high harmonic generation, which exits the jet in the same way. And of course, the advantage of this process is that you have a tabletop setup to generate coherent, that is laser-like radiation in the extreme ultraviolet or even soft X-ray region. And even more, they are important because they can generate femto to attosecond pulses with this process. So this opens up a large number of applications that can be found in a great variety of fields, such as surface science, atomic molecular physics, spectroscopy, or imaging applications. So to be a bit more specific about those applications, so one very prominent application of tabletop HHG sources is coherent diffractive imaging, where you can image small samples with a very high resolution, which is not easily possible with imaging optics. Another important application for high rep rate HHG radiation is based in coincidence experiments, where you really have to rely on statistics to gather data and find your results. There is application in time resolved photo emission, where also a higher rep rate is more beneficial instead of higher energy systems. So to put this a bit more into context, I would like to lay out the HHG source requirements for specific applications. So as I said, applications that use photoelectrons, such as the photo emission spectroscopy, they typically suffer from space charging. So that means they have to reduce the number of photons, XUV photons per pulse. And to improve signal and statistics, they have to increase the rep rate rather to the regime of around 1 megahertz or above that. So then there are these also mentioned coincidence applications, which have to be operated in a way that less than one event per pulse statistically happens, so that they can really sort out the data. And that means to get reliable data, the statistics has to be good enough, and that means you have to gather enough data, and this can also be achieved by a high repetition rate system. And generally, which is true for all applications which suffer from long integration times, is that you have to reduce your signal to noise rate or improve your signal to noise ratio by using a higher photon flux. So in summary, this means ideally you would like to have a high repetition rate plus high photon flux XUV source. And there, of course, the established Ti-Sapphire technology can only operate around kilohertz repetition rates. And Ytterbium-based laser systems have rapidly grown in average power, and they can easily operate in the megahertz regime. However, they have a bit lower pulse energy compared to the Ti-Saph lasers. And that, of course, brings up the questions on the efficiency of the HHG process. So this has actually been studied a few years ago. So this is a very brief overview over the important phase matching aspects in high harmonic generation. So that means to efficiently generate the radiation, you have to phase match your HHG process. And this is actually written down in this equation here, which has different terms. So you have a term which is related to the dispersion of the atoms and the free electrons. And you have a term which is related to focusing. There's another one related to the dipole phase, which is not considered here at the moment. So as you can see, you have a first density or pressure dependent term, which is basically the gas pressure in your interaction region. And then there is a term which relates to a so-called critical ionization and your actual ionization. And this already shows that only if your ionization is lower than the critical ionization, that is, you cannot ionize your gas too much, then you are able to use this pressure dependent term to balance the focusing term and achieve phase matching in your HHG process. And the important message here also is, it's not discussed in detail here, is that the efficiency of your process is more or less independent of your focusing conditions. And this means that you can use the high rep rate Ytterbium systems also to generate efficiently the harmonics. So another important aspect is, for example, the pulse duration of your driving laser. The single atom response of HHG scales with intensity to the order of 8 or 9. And here you can see if you reduce your pulse duration, your signal can rapidly increase because you can basically use higher intensity before you ionize your gas too much. At the same time, also the cutoff increases for the same reason, because you can use higher intensity. You have a larger ponderomotive potential in your HHG process, and this actually dictates the cutoff wavelength. And another way to increase your photon energy or generate shorter wavelength radiation is to use a longer wavelength driving laser, because this ponderomotive potential scales with lambda square. And actually 2 micron lasers are a very interesting aspect to go into the water window. And if you are interested, my colleague Christian Geider also has a talk in this week's conference on AFS 2 micron laser systems. So that means phase-matched HHG with fiber lasers is possible. We have learned that tight focusing has no effect on the efficiency. The only thing we need to have right now is a high average power ultra-short-pulse laser. So, and as I said, Ytterbium-based laser systems are capable of providing that, but typically the pulse duration is on the order of 300 femtosecond. And to reduce that significantly, typically schemes relying on a post-compression are implemented, such as this capillary-based compressor shown here. And basically you send your pulses into a noble gas-filled fiber, hollow fiber in that case. Self-phase modulation happens, and then you can compress your pulses with chirp mirrors easily. And with this approach, sub 30 femtosecond pulses at a few hundred watt of average power have already been shown. And very recently, the concept of multipass cells, which relies on the same physics, more or less, but is way more efficient, demonstrated already kilowatt level sub 30 femtosecond or 30 femtosecond pulses. So generally, the scheme is very flexible, so you can adapt it to a great variety of pulse parameters. So that means you can basically use that for any laser system available. And of course, this approach is average power scalable, which is important to make use of even higher average power, which have become available recently. So if it's necessary, this approach can also be extended to a second compression stage to further compress the pulses down. So with this technique, more than 200 watt sub 7 femtosecond pulses have already been demonstrated. And also recently, 3 millijoule, 300 watt sub 10 femtosecond pulses were achieved. So the XUV source we present here actually is one of the most powerful sources in the world. So this is, I would like to start with this overview graph, which shows the average power in a single harmonic over photon energy for different realizations, laser systems, and publications. And actually what I will show in the following is that our source that we show here in this spectral region actually is the most powerful in the world. So generally, you can see that fiber laser driven sources have now more or less up to a bit more than 100 EV shown the highest average power of this coherent XUV sources. So as I said, the source has been built at Active Fiber System. Active Fiber System is a company that has been founded in 2009, and our mission is to rapidly transit from research into reliable, commercially available systems. Our main market is found in research, from fundamental research, materials processing to life science. And today we are the technological leader for high power, ultra fast fiber laser systems. We recently moved into our new building, which you can see here on the picture, with more than 1,500 square meter lab space and more than 1,000 square meter of office space. And as you can see, over the recent years, we have been growing rapidly. So the system that I would like to present today relies on two of our main products. So first of all, our compact 100 watt 1 micron laser system combined with a high power XUV beamline. And of course, if you're interested, there's a great variety of other products, 2 micron or fuse cycle and CP stable systems. So if you're interested, feel free to have a look on our website. So the XUV beamline that I would like to show in this particular case has been optimized for energies of around 70 eV and 90 eV. But as you can see, we are able to provide a great span of optimization parameters. So we can go to very high average power, lower energy XUV sources up to 150 EV sources with very flexible pulse parameters. So there's actually a new website that we launched. So feel free to join and have a look. And also there's a virtual lab tour. So if you want to have a look at our labs, visit afs-jena.de. So the major or the front of our XUV source is our compact 100 watt laser system. It can deliver energies up to 1 millijoule with very short pulses of less than 250 femtosecond. Great flexibility in pulse parameters, repetition rate. Everything is software controlled and remote monitored, and it has an excellent stability and pulse parameters delivered. So this system actually is combined with a nonlinear compression setup. So the laser system actually is placed here. Then the pulses of this 100 watt laser are sent into this nonlinear compression unit, where we have more than 60 watt, less than 40 femtosecond pulses with more than 120 microjoule of pulse energy. And actually you see that this output is extremely stable. So this is a measurement actually done at the customer side, which shows an excellent average power stability of only about 0.1% of RMS fluctuations. So these short pulses are then focused into a gas jet, which is placed here. Then we have a separation chamber, and finally the XUV output is sent towards the actual experiment. So as I have said already, that this source has been optimized mostly for around 70 EV and 90 EV of pulse energy. And here in this table, we show a few exemplary photon fluxes that we were able to generate with this source. And we have examined them at 70 and 90 EV, but also went to 100 and 110 and 130 EV. And actually, the achieved values are in this range are world record values, which has actually been shown already on this graph in the beginning. So this source actually also shows a very excellent long-term stability. So here we have done some long measurements on the HHG output, and you can see that this is the 70 EV case, this is the 90 EV case, that in both cases the stability is around 1% over this time span of a bit more than 1 hour that has been measured. So as I said in the beginning, this system has been delivered to the university in Delft within the LINX project, which we are a part of together with ASML. And if you want to learn more about this project, there's a nice website on it. And actually what I would like to show is what the partners in Delft are trying to do with our source. So we have shipped the source to Delft and they are starting to implement the experiment. So this is how it will look like. So we will have our laser here, our high harmonic generation beamline here. and then it goes to the experiment of the customer, and they actually plan to do various coherent or other imaging techniques to have a deeper insight into wafers used for lithography and in the semicon industry. So as I said, if you want to learn more, feel free to join us. We have a virtual lab tour. You can have a look at this kind of laser system, also on our bigger laser systems, such as the Eli Alps HR2 laser. And it's very interesting, and you can have a look at how we work at AFS. So to conclude, I have shown that based on our compact 100-watt laser system, we can build a very efficient HHG source with flexible parameters, with a compact design. And this source generates a record high photon flux at 18 nanometer and between 10 and 12.4 nanometer. And to put this into numbers, at 18 nanometer, the source delivers more than 3 times 10 to the 11 photons per second in a 1% bandwidth. At 12.4 nanometer, it's still more than 3 times 10 to the 9 photons per second at a 1% bandwidth. And even at 10 nanometer, we still have more than 10 to the 10 photons per second, also in a 1% bandwidth. So that means on a very compact footprint, you can have the most powerful XUV source to drive your experiments. And with that, I would like to thank you very much for your attention.